So thank you very much for joining us for another MAS Microanalysis Society webinar. We have in one of our very active society members presenting this webinar. So today's speaker will be Dr. Chet Parrish from Oak Ridge National Lab. He is one of the staff members for R&D in the Radiation Effects and Microstructural Analysis Group of the Material Science and Technology Division. His research involves electron microscopy in many different flavors to solve problems in materials for the nuclear energy systems. Chet has been, as I mentioned, a very active member of the Microanalysis Society. He's been a member since 2004, and he's currently serving as a secretary of the MAS. So we're very happy that he was willing to present a webinar. And so today he will talk about TKD 101, an introduction to transmission Kikuchi diffraction. And so with that being said, I will hand over to Chad and have him take us from here.
All right. Thank you very much, Annette. I appreciate it. Apologies to everybody who dialed in 2 weeks ago. My slides got hung up in export control, so I wasn't allowed to show them, but we're good to go today. I haven't uploaded them to this webpage yet, but I'll do that Monday or next week. So if you're interested, you'll be able to download a PDF at this website here. Anyway, so just a quick reminder from our society president, it's the time of year when we need to do membership renewals. So remember, things like this webinar are one of your membership benefits. So please do renew your membership. And then first, just very briefly, acknowledgements. Most of what I've done here is Office of Fusion Energy Sciences, or what I'm going to show today, but along with Office of Basic Energy Sciences and Office of Nuclear Energy have supported various bits and pieces of the work that we're going to show here. So what I want to talk today is just kind of give you the flavor and give you a starting point, right? It is completely unrealistic for me to help you become an expert at transmission Kikuchi diffraction in a 1-hour seminar. You know, that's not realistic. That's not my goal. So if you take 3 things away from this talk, I want you to be able to identify when TKD is the right tool for the job. You know, that's item number 1. Second, help you know what the limits are and what the advantages are. And then last, to recognize some of the most common artifacts, right? Maybe you won't ever do TKD, but you'll be reading a paper or you'll be reviewing a paper. And I want you to be able to spot something that's a problem, right? In order to help you at least know what the artifacts are, even if I can't make you an excellent practitioner in 1 hour. So those are my goals. So first, sources. Every figure in this talk is something that came out of Oak Ridge. That's just a copyright issue. So there are beautiful figures in the literature that were published before I got into the field of TKD. You won't see those pictures in this talk. I apologize. I'm not trying to make short shrift for the people who did the foundational work. This is simply a matter of, I want to post these slides for you to download. And if I'm using other people's copyrighted figures in the slides, that gives me headaches. And then second, I'm going to try and stay vendor agnostic to the maximum amount possible, rather than drilling into details, because there are going to be different people watching this seminar who are using equipment from different vendors. And I want to try and be as broad-based as I can and not drill down into the details of one vendor versus another vendor. All right, so just very briefly, I imagine everybody who's watching this knows what EBSD is, but we've got an SEM. Inside the SEM, we have an objective lens. We have an X-ray detector. We have our EBSD detector, which is a phosphor, right? We have forward scattered detectors, you know, 1 or more around that phosphor screen. We bring an electron beam in. Oh, let me turn my pointer to the laser, and hopefully that will be easier to see. So we bring the electron beam in, we diffract the electrons come out as Kikuchi bands, and we get a pattern on the electron screen. Right, so that's the basics of EBSD. I don't want to get lost into the details here, but what we're going to be talking about today is just going to be variations on this theme. So now EBSD, hopefully we all know, really beautiful capabilities. We can look at a material here. This is just a piece of tungsten that was exposed to a plasma, and then different grains on the surface evolved into different shapes. We can see different grains have different orientations coming out of the page, right? So this is just some of the most basic information we can get from EBSD. We can go in and we can look at the surface orientation of different grains, label them according to the morphologies, and start seeing how different surface orientations led to different morphologies. Just a hint of the amount of information. The sheer number of experiments you can do with EBSD data is mind-boggling, and people are constantly thinking of new things. So, you know, there's tremendous amounts of information we can get with EBSD. We can look at surface orientations, we can look at orientations in plane, we can get pull figures and texture. So there's all sorts of things we can do with EBSD. But the question, of course, is, you know, advantages and disadvantages, right? So EBSD, you know, very high throughput, you know, tens to thousands of points per second. Precision is very good, you know, from one pixel to the next pixel in your EBSD scan. You know, deep sub-degree if you're doing everything well and you're setting your camera parameters. And the accuracy compared to the outside world is a few degrees, but that's not bad. You know, good phase differentiation if the space groups aren't too similar. You know, disadvantages, you know, EBSD, you know, a few hundred nanometers on a good day and a good sample, you know, microns on a bad day with a bad sample. So what do we really want? What we want is a technique that has the same advantages but better resolution. So that's where transmission Kikuchi diffraction comes in. So earlier, one of my main goals for this talk for people to take away from this is when is TKD the appropriate tool? And when TKD is appropriate is when you need EBSD type information, but with fine spatial resolution. That's when you do TKD, right? So if we look at EBSD, you know, the spatial resolution in EBSD, you know, it will depend on whether you're looking at a feature that's along the tilt axis or across the tilt axis. So this grain A and B here, you have better spatial resolution than C and D, simply because of the tilt, you know. So, but your spatial resolution is mostly going to be determined by the atomic number and the beam voltage. Not the probe size is generally a second order effect with a good field emission instrument. So I did some casino simulations using the Sherbrooke code, and then just parsed out their bizarre data files and plotted as 3D iso surfaces. So this is a 70-degree tilt on molybdenum from 10 to 30 kilovolts. And we can see that from 10 to 30 kilovolts, we get a much larger beam broadening. Now, all of these electrons down at the deep part aren't really contributing to your EBSD, but just sort of qualitatively, as that blooming of the electrons gets bigger, you can see that the spatial resolution is degrading. You know, so that's sort of one of the first things to keep in mind about spatial resolution, you know, is it's an effective beam voltage. And if we do the same thing at different atomic numbers, so we hold the energy constant, we go from silicon to iron to moly to tungsten, we can see a much finer spatial resolution. So resolution in EBSD is going to be a function of the beam energy and the atomic number, the atomic density. But, you know, again, what we're really interested in is how can we get finer resolution? So what we're doing here is we want to work in transmission mode. So at the very highest level, what we're doing in TKD is we have our objective lens in the SEM. We bring a beam down onto a thin sample, and then we catch the diffracted electrons coming out of the bottom of the sample. So rather than EBSD, where we're looking at the electrons that are coming back out of the beam incident surface, in TKD, we're looking at the electrons that are coming from the beam exit surface of a thin foil. So what we've got here is an SEM column, FIB column with an EBSD detector coming in from the side of the FIB, and then we've got a thin sample holder. There's a small thin TEM grid clamped in there holding the sample. So the electron beam comes down, and then we catch the diffracted electrons on the EBSD camera. So here's what I tried to summarize to one slide so that when I post the slides and you download these, you can just kind of look at this. So first of all, it's not TEBSD. We're not using backscattered electrons. So it's transmission Kikuchi diffraction. So you want a field emission SEM, we need a lot of current in a small spot. want good stage and room stability. You aren't doing TKD unless you're making very fine pixels and very high spatial resolution maps. So if you're getting drift, whether because the temperature in your room isn't stable or your SEM stage isn't stable, you're not going to get good data. So what we generally do, tilt, rotate, translate the stage, insert the detector, get everything set up, and then take a break, let everything settle down. So I like to work on the weekends or in the evening, go get coffee, go get dinner while everything settles down. And that will really improve your data. And our system in particular that I do all of my TKD on is actually limited by the acoustics in the room. It's a high bay with 6 electron microscopes in it. So we're limited. People are walking past and rolling carts, and liquid nitrogen dewars is the limiting factor for ours. So it really helps to have an on-chamber plasma cleaner. Carbon contamination is a real problem when you're doing TKD, simply because you're putting a huge number of electrons into a very small area, which is a real recipe for getting scan boxes. You want the best EBSD system you can get your hands on. The signal is very weak, so you want high sensitivity and good pattern averaging, usually, in order to get good TKD patterns. So your holder, you need to clamp a TEM sample firmly, but without shadowing the camera. So, you can either improvise or buy TKD holders. We just end up buying them from one of the vendors. It's a lot simpler than trying to jury rig something ourselves. So sample, you want a thin sample with a reasonably uniform thickness. And if you can, you don't want to have, big changes in atomic number, but sometimes the sample's a sample. And then here's another hint that sometimes people look at me funny. Always save the patterns. So my argument is labor is expensive and hard drives are cheap. So save all the patterns always, because you never know if you're going to want them. And you don't want to have to come back and repeat the experiment. For all you know, you might drop your sample as you take it out of the SEM and ruin your sample. And if you haven't saved your patterns, but you need to reanalyze something, then you're really out of luck and you have to go back to remaking the sample. So hard drives are cheap, labor is expensive. Always save all the patterns when you're doing TKD. So when do we choose to use this technique? So if your grain sizes are small, and small is hard to define. I wrote 500 nanometers, but that's arguable. It depends on many factors, but basically when EBSD isn't giving you the information you need to think about TKD. So if you've already made TEM samples, we're really a TEM lab. The reason we do TKD is we're already investing the time and the effort in making good, thin specimens. So the marginal cost of doing TKD to complement our TEM is very small. It costs a lot more money to sit in front of a fib for 8 hours and make a good thin sample than it does to put the sample in the SEM and take a TKD map for 1 hour. And then if you want to do correlative crystallography with your TEM or your atom probe, something we do all the time is we look at grain boundary segregation in the scanning transmission electron microscope by using X-ray mapping. So then just dropping that sample into the SEM after you've taken your TEM data, you can get the things like the grain boundary misorientation for a very marginal increment in effort. So these are your main reasons why you would want to choose TKD. So here's our basic geometry. So we've got our objective lens, the beam comes down onto our thin sample, and then the scattered electrons come and hit our EBSD. So here's just a chamber scope image, sort of showing the cartoon version to the actual version. So, that's typically going to be in the order of 5 to 10 millimeters. If you're an instrument owner, if you're the instrument PI, don't let just anybody do TKD. Make sure it's somebody you trust not to bonk samples into your pull piece before you start unlocking the TKD holder and letting people use that. So generally you want your holder really as far in as you can get. You can see that we've got a little booster seat here that raises the holder up so that the detector can be inserted fully and doesn't bonk into the sample stage here. So you need to think about your geometry just a little bit. So I don't know if you guys are seeing me on the screen, but if you have this tall sample, there's probably going to be a small amount of vibration, but that's a good trade-off. Getting the detector in closer probably outweighs any small increment of vibration by putting the increase in height there, simply because you can get more of reciprocal space onto the camera. So, definitely think about things like, how tall your sample needs to be and how to arrange it. So we've got 7 slots here, 1 in the middle and 6 around the perimeter. We always want to use one of the perimeter ones and not the middle one, just to make sure we can get the detector in all the way. So, and then, illustrating here. So we've got our sample, and we look at it in the SEM. So here's our TEM grid. Then we zoom in and we can actually see that we've got the small TEM sample there. I'm going to talk about this later, but one of the things you'll notice is we cut these as windows with thick ribs around them to minimize the bending. Bending can be a real problem, especially if you want to look at things like strain in your sample. And then from there, we get our TKD pattern. So one of the things that's actually very rewarding and lets us know that TKD is doing a good job is we really can match information between TEM and TKD. So this is a bright field STEM image. And here is the inverse pole figure map off of TKD. And then if we look at a couple of these features, we can see that that grain right there is that grain. We've got a little shape there, that's him. And that shape right there is that. So, a couple things that also kind of jump out. There's a very subtle shift in color right there. That's probably a very low angle grain boundary from there to there, even though just in the TEM, it actually looks like a fairly high angle grain boundary. So this is one of the things that TKD really buys you, is you're actually getting the true crystallographic information and not the semi-qualitative look you get by not, just in TEM. It would be a horrible tilting experiment to measure the difference in angle between those 2 grains in the TEM, but with TKD, this is probably a 30-minute map right here. So in addition to matching what we're going to take as our baseline truth, the TEM data as baseline truth, that also gets us new information that's very valuable. So, and then coming into a couple considerations for geometry, there are a few choices you really need to make, and I can't tell you what numbers to use. You're going to have to optimize this based on your specimen holder, your specimen, your electron microscope, and your EBSD system. But the 2 biggest ones are going to be the working distance, the distance from the objective lens to the sample, and then the back tilt here. So, if we take the definition of tilt for EBSD as positive, if we say that when you're doing EBSD, you're at positive 70 degrees, we're typically at a negative tilt in TKD. So somewhere in the -10 to -20 is a pretty good first guess. Somewhere, and again, this really depends on the system, so don't quote me too much on the 8 millimeters, but somewhere in the vicinity, 5-10 millimeters is going to be a good start in terms of figuring out where, what geometry to start with. And again, for my first guess, I always go to the maximum KV and a very high probe current, just because this tends to be an electron-starved technique. We tend to have a weak signal, and we're trying to push more frames per second through the camera. So more KV and more electrons tend to really help. And again, there are exceptions to all of this, but that's generally our first guess when we're trying a new experiment for the first time. So just to kind of illustrate, so we've got a pre-tilt and a stage tilt here. So this particular holder is pre-tilted -20 degrees. So with 0 stage tilt, it's actually 10 degrees on the holder. And then we go to 10 degrees on the stage, which is -10, 20 degrees on the stage, which means the sample's dead flat. And then we can go 4, 6, and 8 millimeters. So this is just a piece of silicon is the sample. So we can see that we're actually moving that 111 pole around, and then the pattern center actually is off the top of the camera, which can make your indexing a little bit funny. And then as we either increase the working distance or increase that tilt, we bring that pattern center back onto the camera. So there's a lot of considerations here. And, and when you first start doing this on a new system, it's probably worthwhile to take a known single crystal and actually do some of these experiments. So this was what's called a MagiCal sample, which is just a calibration standard you can purchase. And we happen to know that the y-axis in the EBSD coordinate system was 1, 0, 0, and that the X and Z were 1, 1, 0. And we get within a few degrees of measuring that. So that actually gives us some confidence in what we're doing. And again, the first time you do TKD on a new system, I really recommend putting in a known single crystal and doing these measurements just to verify that everything's working and you're not going to embarrass yourself and have to retract a paper in a year because it was indexing funny and you had no idea. So I'd really encourage you to get a known single crystal of some sort and validate your system before you get to work. So, and then in terms of the geometry, it's not hard. In fact, it's hard not to end up with some shadowing. So with the stage tilt here, I think I might have mislabeled that, but if you have not enough pre-tilt, the sample itself is actually going to block some of the electrons. So what we're getting there is shadowing from the sample itself up at the top of the camera, which can confuse the Huff transform and confuse the indexing. So what we're getting there is a shadowed region on the detector that just looks funny. So that's something to worry about. And this was a really difficult sample. It had tendrils right at the surface. So we were optimizing the fib to make those tendrils very thin. But what we ended up doing was making thick ribs. And then one of the things we did is we actually downset the sample rather than putting it in the center of the FIB grid, put it way off down at the bottom so that the amount of shadowing coming off the OmniProbe grid was minimized. So you definitely want to be thinking about while you're making your sample, how it's going to look inside your TKD holder, and make sure that you're not getting things that are going to shadow regions of the camera and interfere with your indexing. So if we look here, we've got the that's TEM images, we've got the pattern quality map, we've got the indexing. One of the things we see is along this left side of these TKD maps, we're actually getting shadowing from one of those ribs in between the windows. So what that shadowing is it's actually blocking part of the camera, and we're getting bad indexing. That, can I scroll it? So those dead pixels along the edge are actually where one of these ribs are blocking the camera. So always be thinking about the geometry while you're making your specimen in order to minimize that sort of effect and get the most real estate on your sample possible. So some factors to consider. This is mainly for you guys to look at when I post the slides to download, but beam current, beam energy, working distance, back tilt, and camera binning are going to be your main considerations. And every one of these is a trade-off. There's not going to be a right answer for any of these. It's going to be a matter of, are you going for spatial resolution or speed? Are you getting contamination? Are you getting drift? There are a bunch of things to think about. So again, in general, I'm always working at 30 kV. It's very rare, less than 5% of the time I'm not working at 30 kV, simply because the higher energy, you're going to have less spread through the thickness of the foil, so you have higher spatial resolution, less drift, faster acquisition. Those are good trade-offs to make. I tend to work at a very, at high single digits of nanoamps to, 2 nanoamps generally, simply because with modern instruments, you can still make a very fine probe at a very high beam current, and being fast, you get less, things like less drift, so working distance is the one I found seems to make the smallest effect of any of them. Basically, you'll find what a good working distance on your instrument is and basically stick within a millimeter of that. So the back tilt, I usually work around -20 degrees, but again, that's very system specific. And then camera binning is going to vary experiment to experiment. There's no way to have a rule about the binning on your EBSD camera. So, and then another point is you can sacrifice reciprocal space for indexing. If you're getting things like shadowing due to the sample holder, you can always use a smaller Huff transform, and especially with low symmetry crystals, a smaller Huff transform can really cause some headaches with indexing. But if you're getting false bands in your Huff transform, that's going to possibly confuse your algorithm. So you may have to fiddle with whatever your vendor's Huff transform region and parameters are, especially if you've got a sample that's giving you some artifacts on the camera. So again, that's too much detail to get into today, but sometimes you have to be willing to trade Huff space for camera artifacts. So in terms of sample considerations, thinner's better. Usually if the sample is a little too thick, you lose resolution and you lose band intensity. If the sample's too thick, you don't get bands and you aren't doing TKD. Now, if the sample's too thin, which is not a common problem, let's just be honest. If the sample's too thin, you're going to get bending, especially if it's, say, a polycrystal or something nanocrystalline, which is what you're most likely to want to do TKD on, right? You know, you can have a lot of retained strain or stress that will make the sample bend. And if you want to look at things like misorientation inside a grain, you know, then you have to ask, am I seeing bending in my foil because it's too thin, or am I seeing actual features in my sample? And then that's a very tough question. So if the sample's too thin, you might get weak diffraction. You can always cut the KV to ameliorate that, although that's going to cost you some of your excitation of how hard the electrons hit the camera. So that's going to cost resolution and speed. And I've got a slide later, but multi-phase systems where you have high and low atomic number together, this is a real problem. And sometimes you just have to gut through it. Maybe even take two maps at different KV and then put them together somehow. You know, so multi-phase systems are a true challenge. And surface quality is all important. You know, the TKD signal arises from the last couple nanometers at the exit surface of the foil. If you fib at 30 kV, you're going to get terrible TKD, and there's just nothing you can do, right? You know, if you're using focused ion beam, finish at very low energy, the lowest your fib will reliably give you, which may be 2 or 5 kV, depending on the generation of your fib. If you have something like a nanomil, where you can go in at 900 EV with argon or 700 EV with argon, absolutely do that. You know, maybe even cut the sample a little thick and then nanomill it for half an hour to really clean off the surface. So in my opinion, the biggest single factor for whether you have a good day doing TKD or whether you're pulling your hair out and crying at the end of the day is the quality of the last 5 nanometers of the sample, the last 5 nanometers of the exit surface of the foil. It's all about the sample quality more than any other one factor is going to control whether you're having a good day or a bad day on TKD, at least in my opinion. If you want to argue with me, my email's on the slide there. So just as an illustration of surface quality effects, so this is a sample that was cut with the focused ion beam. It contained tungsten and a titanium-based ceramic in it. So, you know, for the big, heavy atomic number tungsten, it wasn't a big difference between as fibbed and polishing with a low energy argon. But then we go into that lower atomic number ceramic, and it's a huge difference in terms of the quality of the patterns. So, you know, this is an important point that it's all about the quality of the sample. You know, if all of your patterns are terrible, you either have to sit and average many times on each pixel, or you just get bad indexing. Right? If you can spend an extra 30 minutes cleaning up your sample with a low energy ion beam, you're going to take far more data and have much better data and more reliable data. So, you know, surface quality matters more than any other single factor in terms of TKD success. If you take one thing away from this talk, let it be that. And here we go with sample thickness effects. So this is the best terrible example I could find. So this is a silicon carbide matrix. Silicon carbide is very low atomic number, very light, and it's full of actinides and fission products, which are very heavy. So what we've got, you know, we've got bright field and high angle annular dark field STEM. We take an X-ray map and we're finding uranium and palladium in this region. So these are huge high atomic number regions of actinides and fission products. And then we do the TKD, and the silicon carbide is beautiful, but these uranium carbides and palladium silicides are just giving us horrible TKD. You know, the palladium-based one didn't even index. Now this one, whole different topic for a whole different day. That's actually silicon carbide right there if you compare it to the STEM, but it just misindexed because they had a similar looking zone axis. So in terms of misindexing artifacts, that's its own talk. But, you know, so what we've got here is just, you know, we've got pretty good patterns on some of the uranium carbide, but where it got a little bit thicker, we ended up not getting good enough patterns to index. Whereas here on that palladium silicide, uranium palladium silicide, I should say, it was simply too heavy and we weren't getting anything. You know, so when you have low atomic number and high atomic number, that's a real challenge in terms of getting good quality data, and you're going to struggle. And I don't have a great general answer. You know, it just depends on how you're making that particular sample. All right, so now I'm just going to run through maybe in the next 15 or 20 minutes, a couple problem solving examples, just to give a flavor of some of the things that we can do with TKD. So carbides and reduced activation ferritic martensitic steels. So back in the 50s, before people knew how to electropolish, they would use what's called replicas to do TEM. So polish your sample, etch your sample, and then your carbides stick a few nanometers up above your polished matrix. The matrix in this case is BCC or BCT iron chromium. Then evaporate carbon down, and then that goes down conformally over the precipitates. And you etch, again, you do a deep etch, and that carbon film will float off, and it's got your precipitates embedded in the film. So then you can stick that in your TEM or in your SEM and actually see those precipitates that have been separated out from the matrix. One of the reasons we're interested in this is our matrix is going to be screamingly hot radioactive because it's been in the reactor. So, you know, if we can actually reduce the volume of the samples, that's going to help us a lot. And then plus it's also hard to measure an embedded precipitates chemistry in the TEM because you've got matrix on either side of it is another reason to do this. So one of the things we did is we had these replicas for the TEM and we said, you know what, we bet TKD would work on these. And it turns out it actually works quite beautifully. So again, remember what I was saying earlier, the most important point is your sample quality. Whenever we put one of these samples in upside down so that the exit surface of the sample was the carbon film and not the carbide precipitate, we didn't get patterns. But then we simply pull it out of the holder, turn it upside down, and then the carbides are facing the diffraction camera and the carbon film is facing the objective lens. We got beautiful patterns. So again, I cannot emphasize enough, it's all about the last 5 nanometers of the sample on the side facing the detector, whether you're going to have a good day or a bad day doing TKD. So one of the things we actually did, I'll put the citation there, is we were actually able to go in and identify multiple different precipitates. So this is a nice big map, something like 16 by 14 microns. So this, we got over 1,000 precipitates. So this ran over a Christmas holiday weekend. So again, when you've got huge maps, this was something like a 20 or 30 hour map. And we let the sample sit in the microscope for more than a day. And because it was the holiday, nobody was in the building, nobody was opening and closing doors, nobody was riding the freight elevator. Everything was nice and steady. So when you're doing a really excessively heroic map, you know, with millions of pixels in it, you know, it's all about the stability of the stage and the focus. So we were, and then just to prove that we knew what we were doing, we actually went in and we found some of these precipitates. And again, always save the patterns. I said earlier, always save the patterns. We were able to go in and actually pull patterns from all of these precipitates. And then we were able to find the same region. And again, there was a nice scan box where we took the TKD map. So we were able to find the map in the TEM and then actually go in and take either convergent beam electron diffraction or high resolution TEM for the ones that were too thin for seabed and verify the indexing between TKD and TEM was the same. So, you know, this is just one example of, you know, a problem that in TEM, each of these getting it tilted in and the seabed acquired and indexed or getting it tilted in and doing the high resolution, that's, you know, 30, 45 minutes per sample. You know, when you're trying to tilt a 30 nanometer particle onto a zone axis, that's not a lot of fun, right? That's not very fun at all. Whereas here, it's less than a second because we're just going across with the TKD probe. So we went from 5 particles a day to 1,000 particles a day. So, you know, that is a huge win. And especially if you're trying to do materials engineering, one of our goals with this is as the samples come out of the reactor, we're going to do these replicas and we want to be able to compare before and after irradiation and get statistics and see if things like changes in phase fraction are occurring. And you can't measure changes in fraction when you're n equals 10. You need n equals 1,000 to get those kind of statistics, right? So this is a case where TKD really shines, the ability to go from a single heroic small experiment to big data. Then here's another interesting example. This is the same concept, just on a different material. Here, look at these precipitates. These are banana-shaped precipitates because this was about the first experiment we did on a new SEM, and we hadn't figured out how to properly align the column. Once we practiced getting the wobbler because this was almost at the top end of the beam current. This was several nanoamps, and getting a very fine probe with a very big beam or with a very, very big current isn't that easy. So with a little bit of practice and getting the wobbler cleaned up, all of these snapped in and became very sharp. So that's just another thing to worry about, is your alignment has to be very good in order to see very small particles. So that's just another one of the little gotchas for TKD, is make sure your alignment is dead on. All right, so now as a second example, tungsten nanotendrils. If you take a piece of tungsten, you polish it, and then you expose it to a helium plasma in the right temperature range. It doesn't have to be tungsten. Almost any metal that people have studied, this will happen to if you get into the right homologous temperature. It'll actually grow fur. So that's 200 nanometer scale bar. So we actually grew fur on tungsten. And that's not necessarily easy to understand, how this sort of extremely non-equilibrium structure can grow. So one of the things we did is we just brushed these off onto a carbon film and then did TKD on these. So what we've got here is we have that single tendril, and then did TKD here. And then we have patterns E and D just to show examples. And they're not great, but they're not terrible. They're certainly indexable. Then this is an 8 nanometer pitch. So that's actually a 16 nanometer, possibly even smaller grain boundary we were able to see with an SEM technique. So that's exciting. This was one of the first TKD experiments we did here at Oak Ridge. So actually being able to get that kind of information, really made us feel good. And like, this is a neat technique. This is something we need to do more of. So what we actually did is you can find the long axis of different particles and plot them on a unit triangle. One of the things we noticed is there's actually no preference, which, for something so non-equilibrium, I guess maybe it makes sense that it doesn't have time to select an orientation, although a priori we would have figured based on dislocation dynamics, something like a 101 orientation. Then come in, do the same thing, but instead of brushing them off onto a carbon film, electrodeposit copper down. So here's another point I made earlier. TKD is pretty good at, or EBSD is pretty good at differentiating phases if the space groups aren't too close. Well, tungsten and copper, BCC and FCC, they actually differentiate very well. So electrodepositing copper down on top of the tungsten as a sacrificial layer so that we could fib it without destroying those tendrils, that was no obstacle to doing EBSD or TKD on these tendrils. So actually come in and find, between substrate tendril interface, tendril grain boundaries, and then substrate grain boundaries, get the orientation distributions of the grain boundaries. I don't have time to get into what the orientation distributions are today. That's something you can look up. But again, this is a technique that if you were doing it in the TEM using convergent beam electron diffraction, you're going to get 3 a day instead of 3 a second, like with TKD. So again, just the amount of crystallography throughput you get at spatial resolutions that used to be TEM spatial resolutions is one of the real advantages to TKD and makes it so exciting. So high burnup nuclear fuel, this sample was kicking about 80 rem an hour on contact. This was a very toasty sample. Which is why it's exciting to do this sort of work at Oak Ridge. So we had the cladding and then the fuel pellets. So towards the cladding, the temperature was low, but the burnup, that is to say the number of fissions, was high. And then as you go towards the center of the pellet, the temperature goes up, but the number of fissions is lower. And we actually get a real change in the EBSD structure in the grain size. So one of the questions what we were interested in is trying to figure out what's going on at the transition between what's called the high burnup structure and then the original structure that we still see at the center of the pellet. So we used our contaminated fuels fib and made TEM samples. And the TKD actually worked beautifully. This was the first TKD we did on this, and it was publication quality. So right up on the cladding where the temperature is the lowest and the burnup is the highest, we looked at the relative grain boundary distribution, and then we went into that transition region where we were going from the high burnup to the large grains, and we actually looked at the grain boundary distributions there, and we were actually able to make some conclusions about how that high burnup structure forms. So again, this is the kind of information that really no technique other than TKD is going to give you. So going in and getting in, a couple 100 nanometer or smaller, than 100 nanometer grains actually get the grain boundary character distributions, is where this technique comes in, and very few other techniques are going to be able to do this. So grain boundaries in tungsten, what this was a piece of high purity, 99.99 tungsten. We cooked it in the reactor for 3 cycles, and it came out, less than 90%. So we burned out something on the order of 12% of the atoms into tungsten, or from tungsten into rhenium and osmium. So we've got all sorts of precipitates. We have big grain boundary precipitates. We have intergranular precipitates. We have denuded zones of precipitates around the grain boundaries. We have voids. So the sheer amount of material science going on in the sample is daunting. So what we did is, from this region of our TEM sample, took X-ray maps, so we can see the tungsten matrix, rhenium and osmium in the precipitates, rhenium and osmium on the grain boundaries, intragranular precipitate. So there's a lot of information here. And one of the questions we asked, we said there's a lot of precipitation at these grain boundaries. That's probably going to cause grain boundary decohesion and result in bad mechanical properties. So, is this a function of grain boundary angle? Could we do something like thermomechanical processing to pick certain grain boundary angles to try and mitigate this? So then we did TKD. This is that exact same region. We actually find that we have both low and high angle grain boundaries that are showing basically the same amount of grain boundary segregation. So that particular mitigation approach wouldn't work. So again, this is the kind of information that's either daunting or impossible to get by other techniques. But TKD, especially when you're trying to combine TEM with crystallography, TKD is such a beautiful technique because you've already made the sample to do your TEM work. So the marginal cost of doing TKD is very minor. All right, so what don't I have time for today? So dynamical modeling, if anybody's familiar with the work Professor DeGraff at CMU is doing, this stuff's beautiful, and I don't know where this is going, but certainly, watch this space. The dynamical modeling is definitely the wave of the future. So data mining, there's been some interesting papers in terms of things like k-means clustering or principal component analysis in terms of basically aggregating patterns. So this is something that we're watching because our patterns are so bad due to radiation damage that if we can use statistically informed averaging methods, this might help us with our indexing. So hardware, CCD is obsolete. CMOS is the wave of the future. Direct electron detectors might be the wave after the wave of the future. I don't know. Detectors normal to the electron beam. There's a lot of neat stuff on the hardware that the vendors are doing. I don't want to get into vendor space because I'm not a vendor, but there's definitely exciting stuff I don't have time for today. Recommended reading. I'm going to put these slides on the internet. You can check those out later. All right. So in summary, TKD is a thin specimen transmission-based SEM technique that gets us EBSD style data with improved spatial resolution, almost TEM spatial resolution. So TKD is simple, but there are some considerations beyond what you need for EBSD. TKD, especially for the work we're doing, is a powerful adjunct to STEM and TEM. That's really where it shines in our work is, looking at the same sample in TKD and in STEM. And again, specimen geometry and most especially specimen quality are the most important things. Any time spent cleaning up your sample with low beam energies or using electropolishing or flash polishing is time well spent compared to anything else. So that's what I've got. And we have about 15 minutes or maybe a little more for questions.
Yes, thank you, Chet. Let's see. Do we have questions from the attendees? In the last session, we had quite a good number. So maybe this time we won't have that many. So far I don't see any. And
my email's there if you think of something after the seminar ends. And again, if you just want to email me or type a question in the box saying that I'm wrong and I'm an idiot, I would love to have that discussion because I don't claim to be the world's greatest expert. I would love to discuss this with other people who are experts on any of these topics.
Okay, we have a question. So Chris Waters asks, can you talk more about the resolution versus KV?
All right. So quantitatively, I'm going to say no, simply because that's an extremely complex question. Qualitatively, at higher energies, the beam is going to spread less. So the lower the beam energy is, the more, if you think about in terms of integrated thickness, as the beam penetrates through the thickness of the foil, at lower energies, the beam is going to spread more quickly. So if you have a 1 nanometer beam coming into the surface, it may have spread out to 10 nanometers at the exit surface, and the exit surface is where the TKD signal arises from. So at higher energy, you're getting out of, away from the classical SEM range, more towards the TEM range. I mean, 30 kV isn't really TEM, but just speaking in broad terms. So long story short, as the energy goes up, the propensity of the electrons to be scattered in a given unit thickness of foil is reduced. So if you can work at 30 kV or whatever the highest energy on your microscope is, you're simply going to have less beam broadening through the thickness of the foil. And again, because the signal arises near the exit surface of the foil, that's where the that's where the beam broadening is worst, is where you're actually getting your signal from. So the higher the energy you can get, the less beam broadening is going to improve your spatial resolution. At least that's always been my feeling. And if somebody thinks I'm wrong, please let me know.
Follow-up question from Chris, but the interaction volume is so much larger at higher kV?
Interaction volume doesn't come into it on a thin sample, right? The KO range at 30 kV for a typical material might be 1 or 2 microns, and we've got a 50 nanometer thick foil. So interaction volume is not an applicable mental construct on a thin sample. If you think about the classical picture in your Goldstein book of the little inverse teardrop, we're only looking at the very tip of that teardrop, and the whole broadening beneath it is not in play because the sample's so thin.
Okay, good. That seems to have answered it. He says thanks. Emma Bullock asks, can you comment on approximately how thin your FIP samples are? A few tens of nanometers? Can you comment on how thick is too thick?
So let me answer the second question first. So how thick is too thick is if you're, not getting Kikuchi bands, or if your bands might start, getting broad with poorly defined edges. So basically, as the sample gets thick, the sort of the qualitative shape of the bands and their intensity relative to the background gets noticeably smaller. So, it's too thick when either you don't have Kikuchi bands or you can't index them. Now, in quantitative terms, it depends on the sample. So the silicon carbide samples can easily be a couple hundred, or at least 100, 150 nanometers thick and give very good patterns. Aluminum could probably be 100, 200 nanometers thick and give good patterns. I don't know exactly. I don't do aluminum. But, for tungsten, probably 50 nanometers is too thick. So it's very much atomic number determined. So how thick is too thick is determined by looking at the patterns. And quantitatively, it's going to be a very strong function of atomic number or density.
Okay, and we have another question by Sean Wallace. Do you have any comments on background routines for TKD?
Yeah, it's so to back up. So background, when you do EBSD, the signal to background ratio is very poor because, where towards the center of your pattern, it's very bright, and towards the edges of the camera, it's dark. So you need some way to subtract out that sort of amorphous bulb shape and get your bands. So the two classical ways of doing that in EBSD is you average over hundreds or thousands of grains and you get sort of the amorphous response of your sample at that atomic number and that density, and you subtract that. The other approach is to look at an individual pattern and apply some sort of blurring function, which is provided by your vendor, and then subtract that blurred pattern from your original pattern. So, I mean, I have found that when I can use the average over hundreds of grains, I do, but simply because things like thickness effects, no fib sample is perfectly flat. So it's very difficult to get a good background. So I tend to use the blurring function-based background subtraction. I mean, I found on both, and I'm trying to stay vendor agnostic, but I will say on Oxford and on EDAX, 9 times out of 10, 19 times out of 20, I'm using the blurring function-based background subtraction, simply because the samples tend to not be uniform enough to give a realistic static background subtraction more often than not.
And we have another question. If you had both a TKD setup in an SEM and a precession electron diffraction setup in a STEM to do indexing, which one would you prefer for getting crystal orientation in a FIB foil? Just from an ease of use perspective, is one better?
So this one is much more opinion-based than fact-based. I would go for TKD unless the grains were very small. PED has a lot more knobs to turn, so you might spend more effort optimizing. PED, you don't know as well where in the thickness of the sample the signal is originating from, whereas in TKD, it's originating from the exit surface of the foil. And SEM is simply easier to use, and generally, I feel like TKD is faster, but PED has its advantages. Certainly, if the grain size was under 10 nanometers, and very especially if it was, say, less than 5 nanometers, TKD might not work, and then you might go ahead and start on PED. So certainly if it's 50 nanometer grains, TKD. If it's 10 nanometer grains, I'd probably start with TKD. If it's 2 nanometer grains, I'd probably start with PED. But that's more of a personal opinion than something clear and well-defined.
Okay, that looks like that's what we have in terms of questions. As Chet said, no, we have one more. What resolution have you seen with TKD?
So quantifying that can be a little bit tricky. I feel like on really beautiful samples in the middle of the periodic table, something like an iron chrome alloy that we've nanomilled the daylights out of, can probably 10 nanometers is not that hard to do. Sometimes you have to say, what is my definition of resolution? Is it a small grain bending in between two other parts of a grain, and I see 2 pixels with a 5 nanometer pitch? So resolution is hard to define, but I think that on a good sample with a good SEM, 10 nanometers should be fairly trivial. I feel like we do that all the time. Getting less than 10 nanometers, then you start arguing about what is the definition of resolution. But and again, it's mostly about the quality of the sample, and then then your next most important question is the quality of the SEM and the room. So it's hard to say exactly what resolution is. I mean, it would be really nice to have, atomic layer deposition, of known thicknesses and that, but, nobody's going to fund me to do that experiment. So exactly what is resolution is probably a question that we should ask, but I think, 10 nanometers isn't that hard to do on a good sample, and it's mostly about the sample.
Okay, do we have any other questions? So yeah, please contact Chat otherwise if something comes up or you watch a recording of this webinar. We will, so this webinar was recorded, and we will also upload it to the MAS YouTube channel, so that's available. And yeah, Chet will also share the slides of this talk. So with that, I want to thank our speaker for this. Yes, other people mentioned thank you for an excellent presentation.
Yep.
And
thank you.
Yeah, please, if you're already a member of MAS, please renew your membership. Otherwise, look at what we as a society can offer you. This is one of the benefits that we're trying to do specifically right now. And yeah, otherwise have a great weekend and thanks for joining us.
Thank you. I appreciate the invitation.